So today, of course, Peter Sterling is going to give the colloquium. Before I hand things over to Adam, who will introduce Peter, we'll just do things as we usually do. So I'm pretty sure Peter's happy to be interrupted. So if you have a question, you can raise your hand, put it in the chat, and Tony and I will kind of keep an eye on things and try to draw his attention to that. Yeah, and okay, I guess I'll hand it over to Adam then.
Okay, thank you. It's a great pleasure to have Peter Sterling, Professor Peter Sterling, with us virtually from Panama.
No, I'm in Amherst, Massachusetts.
That's almost like Panama. I remember being in
almost.
the college area. Hampshire College is like Panama. That's right. Like, I spent a year in the 5 College area. Thank you. Thank you for joining us. Professor Sterling is a professor of neuroscience in the Department of Neuroscience at the University of Pennsylvania. In terms of his research, he's made highly significant contributions to the knowledge about the 3-dimensional structure of the retina, and this served as a precursor for the new area of connectomics. He is an author of 2, I will call them both influential books. I'm going to, the newest book I think will be very influential, just like Principles of Neural Design. His recent book published in 2020, What is Health? Allostasis and the Evolution of Human Design, is the topic of his talk today. One of the things that I appreciate, many of us appreciate about Peter's thinking, is that it is often labeled, I think, pejoratively as teleological thinking, but really we want to understand and explain why things are as they are. And we often have taught students not to think that way, but I think many of us want to understand why things have evolved as they have. And in that pursuit, he has coined the term allostasis for stability through change. As a big fan of Walter Cannon, I have Wisdom of the Body sitting on my windowsill. I like to look at it every once in a while, and we teach about it as someone who studies emotions. What Professor Sterling has done is expand the concept of homeostasis to understanding things about prediction, which is very current in the way we think about the brain. One of the really interesting aspects of inviting Professor Sterling back is he was an undergraduate at Cornell. What year were you, Peter?
This is in my talk. We'll see.
Okay. So I don't want to go far there, but you know, I know he spoke about this yesterday to some students as well. Is that you know, Peter has been able to be both you know, an anatomist, a physiologist, a neuroscientist, and a social activist. And in this past year, where many of us have tried to figure out how to do the work we do in the lab and do good for the world, Peter is an example of how to live that life. And so you're going to talk about your participation a little bit in the freedom rides.
Yes.
And so I think, so I did also want to highlight, so that, you know, from someone who's, you know, been able to innovate examinations of the 3-dimensional structure of the retina to participating in the freedom rides, these are not, you know, this can be the same person, right? You can live both of those lives. And so he, in Current Biology, published in June, Why I Joined the Freedom Rides. I love that it's published in Current Biology. It's a recommended read. And I was mentioning beforehand that we have had a social and racial justice hiring cohort in the past year. And if we had a social justice themed talk series, I would invite you to that. And in that honor, I want to, I'm creating one on the fly right now that to make this a social justice talk. And I'm just really pleased to have you here to present and share your life perspective and work with us. Thank you.
Well, thank you, Adam. And thank you for, and Katie and Linda for helping me arrive here. And I would say that I did arrive on campus at Cornell in the fall of 1958, and I spent 3 years, and it was just wonderful. So it's really wonderful to come back. Well, I wish I was actually there to take a stroll down the green and the bridges and stuff like that. I'd also like to say, since there were, I spoke to the students yesterday, that a couple of the early slides in the talk do repeat the slides I showed yesterday, but they needn't, I hope they'll stay still for the rest, because it's not just a rehash of yesterday, it's sort of a moving on from that. So with that, yeah, let me, so if there are people who do want to chat, I hope Katie will sort of wave her hand or something like that, so I can, because I get, once I get into it, I'm not noticing anything else. So let me share my screen, and yeah, so yeah, oops, yeah, is that working? Okay, let me move this to the side. Yeah, okay, so this is the title of my talk. It's really the same as the title of my book, and which, well, let me just, I will explain as I go. So, let's see, yeah. Screen share, you can see this. Yeah, okay, so my laboratory focused on the fine scale neural circuits leading ultimately to this book with Simon Laughlin, which came out around 2015. And the point of the book was that the human brain is smarter than a supercomputer, but it uses 100,000-fold less energy in space. And of course, and this is fostered by 10 principles of efficient design, and that's covered in this book. And of course, the body uses 80% of the total energy that we take in, and so it must also be efficient. And yet homeostasis, which Adam loves, makes no reference at all to efficiency. It's about correcting errors, and but efficiency, of course, requires preventing errors. So the brain, what happens is that the brain actually predicts what is going to be needed, and it regulates our physiology and behavior to meet them. Now, Joseph Iyer and I called this allostasis. Homeostasis is stability through constancy, and allostasis, which I learned from a professor, a Penn professor of Greek, is stasis, stability through change. So we've recently updated the story. This is an item from Trends in Neurosciences by Jay Shulkit and me a couple of years ago. And now this brings us to this new book, What is Health? And what I try to cover and ask is, what does our species, Homo sapiens, require for a healthy life? And can we achieve this with drugs? And also things like, why did Homo sapiens invest in art? And then I must consider with that question, what qualifies me to comment. My NIH biosketch certainly is a license to talk about circuits and efficiency, but about human evolution and art and music, maybe not. And so what has led me to that is that there has been, as Adam mentioned, an interplay and a tension between my laboratory studies and my social activism. And so the book and this talk really reflect how I've lived. So here we come. Here's Cornell University, 1961. This was my first scientific report submitted to Professor Howard Schneiderman in Stimson Hall. Does Stimson Hall still exist? Yeah? No? Yes, good. As I mentioned yesterday, I came close in this period to actually burning it down. And it's a long story, but fortunately it's still there. So this is my first scientific report. And upon submitting it, I left Ithaca for Mississippi to join the Freedom Rides. And so this is a film clip which emerged when PBS made a film about the Freedom Rides. I was quite surprised to find this. So let's just see. It's a very brief
How about
clip.
you? Can you give me any of your feelings on why you want to take part
This
in
is me.
Well, I want to help establish the right of all Americans to eat together and to travel together.
Why do you think it's your responsibility?
I think it's every American's responsibility. I only think that some are more conscious of their responsibility than others.
So that was about 10 minutes before we landed. And, the train arrived in Jackson, Mississippi, and we were immediately arrested. And then 30 minutes later, we were processed. This is my, I put this portrait on my Twitter page. So since then, I've continued, this sort of social activism in various forms. And so the next incident is, it's the mid-1960s in Cleveland, Ohio at Western Reserve University. And I'm a graduate student in a neuroanatomy lab studying the motor pathways from the cerebral cortex. And I was studying the corticospinal connections in the cat, okay? But I would slip away from my microscope to canvas door to door in Central, which was the poorest Black ghetto in Cleveland. And what I found was that people answering my knock were often limping. They were partially paralyzed. Their face was sagging. Their speech was slurred. And when I went back to the lab, I learned that the proximate cause was destruction of these very pathways I was studying by stroke from chronic hypertension. I realized that my grandfather had lived in Central 2 generations previously when he was a house painter and a member of the Jewish House Painters Union. It was a Jewish ghetto. And I realized that my grandfather had also suffered hypertension and early stroke. So I began to wonder whether hypertension was related to social tension. So the next moment was that and by the way, as I was typing my dissertation in 1966, the ghetto exploded in riots or resistance, and it was the National Guard was called out. It was a real, fracas. Okay, so fast forward to my own lab at the University of Pennsylvania School of Medicine, where I worked for 40 years. I was still slipping away, but now I was slipping away to the library to seek evidence for what are the causes of hypertension. And I was also devouring ethnographic studies to learn how other peoples live. And I was slipping away to visit indigenous communities in Central America. I chose Central America because I discovered it was I could get there faster and cheaper than going down the Brazilian Amazon, which was a fantasy, but this was more practical. So I now live, as Adam mentioned, half of each year in the mountains of Western Panama in a community of subsistence farmers and indigenous workers. These are my neighbors, Oliver and Judith Mendez, milling our sugarcane. And so here's what I learned. First of all, the blood pressures of, because we're talking about hypertension, the blood pressures of foragers and horticulturalists, such as this Nobe family. This is a family that I bypassed. This house, this family is 2 days from the nearest market, and they are waving to us as we pass by, crossing isthmus back from the Caribbean to the Pacific side where I live. So these people's blood pressures are low and they're steady with age. They don't get higher as you get older. And this is true for similar groups in Southeast Asia, South America, and Africa. So when you live with this sort of lifestyle, your blood pressure does not rise, and nor do you have cardiovascular disease. So contrast is in the US, blood pressures rise when children enter school. So this is age down here, and blood pressure rises just around 6 or 7 as children leave their family and go to school. And by graduation, 25% of the pressures are above 140 millimeters of mercury systolic. So, and this reflects sustained physiological arousal. And the rise is steepest for African Americans because they are the most stressed. And that's because Black lives still don't matter. Now, blood pressure, it turns out, responds to every change in mental state. It's not something you have when people say, well, I have a blood pressure of 120 or something like that. Well, this record I discovered in early 70s. It's made in 1969. It's amazing. This is a 24-hour record. This is arterial pressure, systolic above, diastolic below. And I saw this, I thought, my God, it's going up and down all over the place. And what is this? Well, the guy who measured it, he's moving around, going through his day. And this is 3 o'clock in the afternoon. And he's dozing in lecture. His blood pressure comes down from near 120 down to 80 something. And then at this point, he's jabbed with a pin and his brain predicts danger and the pressure goes shooting up. He looks around, he realizes this is a prank from a neighbor, maybe a Confederate, I don't know. And so it goes back down again. And then there are these other unidentified peaks and valleys. And the next identified peak is at midnight when he's sexually aroused and his brain predicts the need for elevating the pressure to participate in sex. He does, it comes crashing down and into a profound sleep, and the pressure goes way down below 80. It goes down here, but something like 60 over 30 or something. So during sleep, the pressure comes down. This is partly regulated by our circadian rhythm. And then the next morning when he's up and about coping with his day, it goes way back up again. So, so this is allostasis. This is dynamic change to maintain the stability of what's needed. So the brain recognizes the context, predicts need, and adjusts the pressure to match. And it provides just enough and just in time. This is, as I mentioned yesterday, the slogan of Toyota's assembly line: just enough material, just in time. So, and I want to point out that this is tremendously wide dynamic range and that the system is extremely responsive, and that is health, is responsiveness is health. So the next thing to notice is that arteries adapt to the predicted mean pressure. So this is the record I just showed. The mean pressure is around 100, and this is what the arteries would look like. There's the cross section of the arterial resistance arteries are sort of sturdy but not overdone, and that's a healthy set of arteries. For a person who suffers hypertension, who has a mean pressure of on the order of 160, this is what happens to their arteries. They hypertrophy, and the lumen shrinks, and eventually you need the hypertension, the higher pressure, just to force the blood through this narrow lumen. And this is just a normal sort of adaptation. If you lift weights, your muscles strengthen. If you keep stretching and demanding the arterial muscles, they also hypertrophy. So the next thing to notice is that all of the mechanisms that raise or lower blood pressure are controlled by the brain. So the brain, first of all, sends nerves to endocrine cells in the kidney and the adrenal that conserve salt water and pump it back into the blood to raise plasma volume. It also sends nerves to the heart to increase rate and contractility, and to blood vessels to constrict. And all of these factors together raise the pressure. Now, there's another item that I was surprised when I learned it, but I guess people who study rat physiology know this, but it's not generally understood that the brain also controls our appetite for salt. And the reason is that if the brain is telling the kidney to save salt water, it better make sure that there's enough salt to do that. And so when when there's an opportunity to or a need for salt, the brain sends us out to find it and to eat it. There's a guy named J.P. Henry who studied this for many years in humans and in rodents, and he concluded that psychosocial arousal induces salt appetite, making a society's salt consumption a measure of its social stress. So anyway, okay. Now, drugs, the standard medical approach to this is to use drugs to block these various mechanisms to reduce blood pressure, to reduce hypertension. But with each one, the brain compensates. So for example, the common drug to start with is a diuretic, and that stimulates the kidney to release salt water and to lower the blood volume. And of course, it does that, but then the heart compensates by increasing its rate and contractility. And you can block that with a beta blocker, and that can prevent the heart from doing that. But then the nerves to the arterial vessels increase vascular resistance. And you can block that too with various mechanisms. One is a calcium channel blocker. And so gradually, there are other kinds of drugs that do related things. And eventually, if you give enough of these drugs, you do get control of the pressure. But now the system can't respond to new predictions. And at my age, I have old men I walk with, like me, and many of them are on beta blockers for hypertension or other cardiovascular issues, arrhythmias. And so as we walk, we're fine on a level surface, but if there's the slightest slope going up, they can't increase. It's difficult for them to increase their cardiac output, and so we have to slow down. So it's a real thing. When you block all these mechanisms that we need, you reduce the possibilities of responsiveness. Now, another point is that all of these drugs have multiple effects. They're not side effects, they're actually effects of the drugs acting on ion channels or receptors and so on. And one example is a beta blocker that being given to prevent heart rate from increasing also raises blood glucose. And of course, many people who have hypertension and heart disease who are taking beta blockers also have type 2 diabetes, and this exacerbates the type 2 diabetes. Of course, you can there are drugs to treat type 2 diabetes. And so you get into a series of drugs and more drugs, and the result is that you have an ill patient, fundamentally ill patient, who is stabilized precariously by polypharmacy. And the problem is that, so I want to consider now, so shift away from the physiology and consider some problems with US health. And then I want to connect that to certain aspects of our neural design, and to mention, to briefly talk at the end what we need to do. So first, this is a graph by Case and Dayton at Princeton University, who've pointed out a couple of years ago that the US death rates are rising for all causes. And this shows France, Germany, United Kingdom, Canada, Australia, Sweden, all coming down. Their death rates are coming down. This is starting from over the last 30 years, 20, 30 years. And they're still rising, as I'll show you later. Where our death rates are rising, these other countries are coming down. Moreover, the rises are steepest for drugs, drug deaths, alcohol, and suicide. This happens to be for men and women, born around 1970, and the rise is steepest. And we call these, I'm going to call these deaths of despair, which was a term introduced by Case and Dayton. And it's fourfold greater, the death rate for males with no education beyond high school. And that's 60% of white males. Now, the deaths of despair arise most steeply for the younger cohort. So here's a cohort born in 1970, and they crossed this 100 deaths per 100,000 line from these drug, alcohol, and suicide at around age 50. But the cohort born in 1980 crossed the same line at about age 35. And I can tell you, I'm not showing it here, that for younger ages, the curve is even steeper. So at the same time, obesity is rising from what I call the rich, sweet foods, which I would call foods of despair for reasons I will explain. And so that's very much paralleling these addictions and suicides. And the curve is very similar when you look at mass shootings, which I call murders of despair. It's basically the same curve. And this reflects, I think, a rising despair that gun control is not going to cure. Now, so now the question is, what causes our collective despair? First, consider our huge brain. It's 3.5 times larger than a chimpanzee, which is our closest surviving relative. Our brain grows slowly during childhood. It uses like 60% of our total bodily energy, and that retards the body's growth. All our resources are going into growing the brain until adolescence, when the brain growth slows, doesn't stop, but it slows, and the resources can be devoted to our somatic development. So this is a graph using data from hunter-gatherers by a very distinguished group of ethnographers. And so this is age from 0 to 80. This is calories, our net production of calories per day. And what it shows is that, at birth, we're sucking up calories. We have no capacity to find any. And even until about age 15, we're just a sink for nutrition and do nothing for ourselves. And then we gradually become able. And by age 20, we can cross that line and begin to just find enough nutrition to take care of ourselves. And at that point, at around age 20, hunter-gatherers join the what's called the work. It's not jobs, but it's going out and foraging and hunting for food. And at this point, I would call this, by comparison to modern life, tertiary education. Children go through high school, secondary education. When they enter this adult world, they are just beginning to learn their trade. And what I think is amazing is that it takes so long. You think people go out and shoot a rabbit and find a nut or a plant, and no problem. But the skills involved are substantial. And so there's a growth of productivity from age 20 to age 45. This is a real career. And people living like this maintain good physical condition, and they remain net producers, taking care of themselves beyond age 60, typically. And so what this means is that for 200,000 years from the emergence of our species, gathering and hunting were challenging careers. They demanded prolonged study and practice, and this lent meaning to human lives. Now, the second point I want to make about the brain is that every brain is different. Our brains specialize, and this is something I talk about with Simon Laughlin in her book, to conserve energy in space. And so the human brain has on the order of 200, the cortex, 200 specialized cortical circuits. And reaching this limit in a single brain, we specialized across brains. So every brain gets a slightly different set of these circuits. And so they're unique for each brain. And then what this does is to confer on each person a set of innate abilities that's unique. Of course, we practice our innate abilities, because that's what's most rewarding. If you're athletic, you practice that. If you're musical, you do that, and so on. And what this does is to produce a community of experts, a hunter, a healer, a navigator, and so on. And so communal intelligence obviously outcompetes a design where everybody has the same set of innate abilities. And the problem is, it makes us awesome as a species, but there are costs. And one is mental distress, and another is interpersonal conflict. This goes with having separate brains with separate opinions, separate needs, and so on. So to benefit from this communal intelligence, we needed to find ways to cohere, and we evolved ways to cohere. And this is achieved by what may be called sacred practice, what words alone cannot express. So our brain invested in costly circuits that go well beyond foraging. This is not just about finding roots and berries. It involves art. So here are cave artists from Indonesia, 44,000 years ago. These are dates that were found fairly recently. And when you look at the cave art from these periods, you realize this is not some, dopey caveman out of a cartoon drawing a stick figure. These were serious artists who knew what they were doing. And the same thing is true for music. This is a cave musician's flute, a bone flute from Germany, 40,000 years ago. And so these, there are other examples. Of course, storytelling and comedy and all kinds of things don't survive for archaeology, but they were probably there as well. Pretty much with these things emerged with our species. This is characteristic of our species. Now, the thing is, if I may, why do we have these? Well, because it's an investment in the brain, because these practices elicit intense emotions, awe, grief, joy, laughter, and so on. And that releases tensions and fosters cooperation so that we can actually use our communal intelligence. Great. So what happened is that after 200,000 years, our communal intelligence produced a steam engine. And in 1769, it was patented by Watt. And of course, that led to, this is 1769 line here, and it led to a very prompt, immediate growth in industry. This is CO2 concentration, and this is the curve. It looks sort of like an action potential, except that action potentials reach a peak and then turn around and come down, and we don't show any signs of this yet. And of course, this is deeply alarming. Now, industry shrank as this grew. Industry really shrank opportunities for challenging activities. And this was recognized that this was going to happen immediately by Adam Smith, who's the father of modern economics. He was a friend of James Watt in Scotland. And he wrote in 1776, he says, the man whose life is spent performing a few simple operations has no occasion to exert his understanding, exercise his invention. He naturally loses the habit of such exertion and generally becomes as stupid and ignorant as it is possible for a human creature to become. Well, I think it's not that we become stupid. The problem is that we're still smart, but we've narrowed the possibilities to exercise our innate gifts. So we evolved to explore the planet, which we did very promptly, leaving Africa, covering all of the planets, all of the planet. And now multitudes punch a ticket or scan a barcode. And so jobs that are learned in minutes or days just don't present a sufficient challenge to really live well. And so there's a mismatch between our abilities and our opportunities to exercise them that helps cause despair. So what links despair to compulsive consumption of food, of drugs, of all kinds of things? Well, we inherited a circuit from worms that drives seeking. Our circuit rewards an unpredicted find with a pulse of dopamine, and you all are aware of this, I'm sure. So here's a recording from a single neuron by Wolfram Schultz, who really contributed a lot to this idea. And here's 10 spikes per second when this is dopamine signal. When a reward an unpredicted reward appears, you get this big pulse of dopamine. So we experience from this chemical pulse, we experience a pulse of satisfaction that allows us to pause in our seeking. And then as the pulse dissipates, seeking has to resume to serve the next need. Foragers find food unpredictably, a root, a rabbit, something like that. They get a pulse. They find comfort also unpredictably, a dry cave, a warm fire. And so they have frequent sources of these positive surprises. We now find food and comfort predictably, without effort or surprise. But the problem is that it's very convenient, but predicted rewards provide less dopamine. And I want to show you the same recording from the same neuron when the reward is predicted. And, there's very little dopamine. So lacking these frequent pulses of dopamine, we grow restless and we seek surprises. And so the problem is when food is predicted, the main surprise has to be more or richer. And so we get these great surges of sugar and fat that evoke surges of dopamine in our brain in various places. And of course, if the surprise is more, the next surprise has to be even more, or it's not a surprise. And so we go from a Mac to a Big Mac to a Whopper. And then the brain adapts to each of these surges by reducing its sensitivity, because that is a standard physiological principle, is that you adjust your sensitivity to what's around. And that's the same story for drugs. We find nicotine, alcohol, cocaine, amphetamines, and opiates. All of these evoke these great surges of dopamine, to which we soon adapt. So drug addiction, I would maintain, is not a substance use disorder. It's called this in the literature all the time now, but it's not a disorder. It's just a natural effort for people to escape their despair, and it doesn't work because we adapt. So what to do? We now treat a despairing population with obesity, type 2 diabetes, hypertension, cardiovascular disease, addictions. We treat them at the molecular level with a panoply of drugs. But polypharmacy is not a plausible route to health. It doesn't work, and it's very, very expensive. So what health requires is, for one thing, social inclusion. Everybody has to feel that their lives actually matter. And so reducing inequality reduces stress and despair, and thus improves health. Second point is that health requires practicing our gifts across the lifespan. Automation now is progressively reducing the quality of jobs. But what we need now is not more jobs, as every politician says. We need to find challenging activities that justify our large brain. The third point is that health requires expanding sacred practice to relieve the tensions that are caused by our innate mutual strangeness. We click now, just a click, for products of sacred practice. We can get Spotify and Netflix and ESPN and Pornhub. But the point is that vicarious experience just cannot substitute for participation. So to conclude, health is responsiveness. It's an adaptation to continual change. It involves predicting future needs, and it minimizes errors, and for that reason, it's efficient. Second, allostasis which includes all these processes that support predictive change. And it started with cyanobacteria, which evolved a molecular clock that predicts the best time to make new DNA, which is at night when the UV is low and there's least damage to the synthetic process. The worm brain incorporated that clock, and it predicts the needs of each organ, and it learns to find the resources. And we've adopted these molecular and neural circuits that were optimized 500 million years ago. And so now we're trying to tweak them. I mean, modern medicine is trying to tweak them, these 500 million-year-old circuits, to fix the problems of the last 200 years. But drugs that block ancient signaling pathways reduce responsiveness. And so the fourth point is that our brains evolved for individualized lives of physical, cognitive, emotional, and spiritual responsiveness, learning across the lifespan. And I think it's our responsibility to live such lives and to help others live them. Thank you.